Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible. I would also greatly appreciate if you consider supporting us as well. So please check the link in the description or click the join button below for more details. My name is Sava, and today we're investigating a key concept that forms the basis of modern machine learning techniques. It can seem a little bit simplistic, but it's still quite frequently used in research and practical machine learning applications. The model we're talking about today is the least absolute shrinkage selection operator, quite a mouthful, so it's most commonly known by the abbreviation LASSO. And LASSO can be considered a modification of ordinary least squares regression when you have got a problem of multicollinearity, or you have got too many variables in your model as explanatory variables and you want to set the least important of them to 0. Shrink them, or shrink them so much that the coefficients are zeros. It is very handy when you have got a lot of explanatory variables, and some of these you need to set to 0 so that they do not skew the results of your forecasts. Also, LASSO can be used to select from a set of candidate variables that might impact your output variable, your response variable, your dependent variable y, those that would be there in your final model, those that LASSO for some specification would reduce to zeros are not going to make it. Today we're learning about the applications of LASSO in Excel. It is actually a machine learning technique that can be quite easily implemented in Excel using the solver technique, and discussing its relationship and its similarities and differences with the ordinary least squares regression. And the task of regression, that is, find an expected or predicted value of a response variable knowing a set of input or independent variables, is what bridges the gap between conventional econometrics, where you talk about different OLS models or its extensions, and machine learning, where the techniques are perceived as more black box and less straightforward, mathematically at least. However, all of these regression tasks can be compared in terms of the loss function they minimize. You all know that the OLS regression has to do with minimizing the squared sum of residuals, minimizing the residual squared sum or minimizing the sum of squared errors over here. And the loss function that we seek to minimize by varying OLS parameters is the sum of differences between the response variable y and some combination of coefficients and input variables x squared. And it turns out to be that the solution can be expressed in a closed form, and this is this matrix solution that we have for the OLS regression. For the LASSO regression, or for the LASSO technique, we start with the same error term. The component of the loss function of LASSO is there in the OLS loss function. However, we also add a penalty term that has to do with the parameter lambda, which basically specifies the severity of our penalty. How much do we want to penalize the model? And here we sum up the absolute values of model parameters, the absolute values of model coefficients. The logic is that if the model falls victim to multicollinearity, the coefficients would be inflated. They would be too high and they could scatter in different directions. For example, if you regress a portfolio return onto two very correlated benchmarks, you could get a result where the one that has the most correlation with your portfolio would have a very high positive coefficient, and the one that is correlated the least with the portfolio will have a very high negative coefficient. To address this issue, and to set coefficients of parameters that are not really that important to zeros, we conceptualize our penalty term as the sum of absolute coefficients. And here, this particular loss function unfortunately does not have a general closed form solution, but it could be optimized numerically using the solver function that is built into Excel. And we might already see that if we set lambda to 0, we'll get back our conventional OLS loss function, and we'll verify it using an example today. As for the significance testing, as for hypothesis testing for the coefficients, we can apply the covariance matrix approach that is developed in terms of OLS and use the model prediction error or standard error of the regression model sigma squared times this inverse matrix we all know and love that gives us the covariance matrix for both models. So we'll be able to test for the significance of coefficients in very similar fashion. So let's now proceed to the task we're going to apply LASSO to, and the task is to investigate the determinants of the return of BlackRock, a very famous publicly traded fund, with respect to 4 major asset classes: large stocks, S&P 500, treasury bonds, gold, and oil, represented by the respective ETFs or exchange-traded products. So first, we need to figure out the daily returns of BlackRock, and we have got 5 years worth of data here, totaling 1,257 return observations. Then we need to code in a constant as a column of ones over here, and then we can calculate the returns for all 4 of our genuine explanatory variables: the S&P 500, the ETF of US long-term treasury bonds, the gold ETP, and the Brent crude oil exchange-traded product. And now we can already use the data that we have to estimate our OLS coefficients using the conventional approach, using the mmult of the inverse matrix, and into the inverse matrix we input a product of transposed matrix of X, including the constant over here, and the same matrix non-transposed, which means that we would not transpose it right now, so we multiply the transposed matrix onto itself non-transposed. Then we close the appropriate number of parentheses, and we multiply this inverse on the right by a transposed X that we have got copied already. And then we close this parentheses, and the final step that we need to take is to multiply this whole result on the right by the vector of the response variables y. And now we can enforce this using Shift-Control-Enter and get our OLS coefficients. And let's copy them down here as values so that we start with the same set of coefficients for both of our models. Now, in terms of the covariance matrix, we need to calculate the predicted values for both models, their error terms, and the respective squared sums. So for the prediction, we can actually efficiently find the predictions for all observations by doing the following trick. We can select this whole column by putting some value in the cell on the bottom, and say mmult, multiplying the whole matrix of independent variables, including the constant, onto the vector of coefficients. And that, if we enforce it using Shift-Control-Enter, would give us the OLS predictions for the whole sample period. And now we can do the same thing for the LASSO coefficients. We can select the whole column, matrix multiply the X matrix, including the constant, onto the LASSO coefficients over here. And we Shift-Control-Enter and get the same predictions as we have copied as values across the 2 same sets of coefficients as for now. And then we'll use numerical optimization to minimize the loss functions for the LASSO models. And now we can calculate the errors. Those would be returns of BlackRock we observe with column locked minus the respective prediction. So the OLS error would be BlackRock return minus OLS prediction. LASSO error would be BlackRock return minus LASSO prediction. And we bottom click it all the way down, get our errors, and now we can calculate our residual sum squared by using the sum squared function. For the OLS, we select the OLS column. That gives us a residual sum squared of 0.1385. For the lasso sum squared, we can apply the same function but to a neighboring column. The degrees of freedom for both models would be the count of our observations, so we can count elements in any of our columns. So let's count the y variables, BlackRock returns, and then we can subtract the number of model coefficients that are over here for the OLS. And for the lasso, they are over here. Now we can calculate model errors. Those would be simply the square roots of the sum squared divided by the degrees of freedom. So the errors so far are exactly the same for both models, given the fact that the coefficients are the same. And now we need to introduce the coefficient penalty for the lasso model. First, we can specify a value of lambda, a value of the penalty. So let's start with the value of 0 to show that the results are equivalent to OLS when lambda is 0, and calculate our penalty as the sum of absolute values of coefficients in the lasso model multiplied by lambda. And we can enforce that using Shift-Control-Enter. We can see that for lambda equals 0, the penalty is 0 by definition, and therefore the loss, that would be the sum squared plus the penalty, is the same as the loss, the sum squared, for the OLS model. And now we can finally calculate the covariance matrices, standard errors, t-stats, and p-values for both models. So for the OLS, we can refer to the error of OLS squared and then times it by the inverse matrix that has x transposed multiplied on the right by x. So we do M inverse of a matrix multiplication result for the transposed matrix of x that we've got over here, including the constant, and multiplied on the right by the non-transposed version of itself. And then we close the appropriate number of parentheses and enforce this matrix multiplication using Shift-Control-Enter. And finally, for the lasso model, we can simply tweak the standard error that we input in there by referring to the error term of the lasso model. And obviously, the results for lasso would have a higher error, as we're also caring about the penalty for positive lambda, so we would have higher errors of coefficients in this particular matrix. We can verify that by calculating the square root of diagonal elements that represent standard errors of coefficients themselves, as the diagonal of a covariance matrix has on it the variance of the respective elements. And then we can drag it down and adjust so that it refers to the diagonal elements. So we carefully drag this around to calculate square roots of the diagonal elements of the covariance matrix. And now, given the arrangement of the matrices we have got here, we can simply copy and paste the results across, referring to the correct elements of the lasso covariance matrix. And now, the only thing remaining are the t-stats, coefficients divided by respective standard errors for both models, and the p-values that can be calculated using a two-tailed t-distribution, inputting an absolute value of the t-stat and the degrees of freedom over here with the row locked. And for the lasso model, we can copy this formula across, refer to the appropriate t-stat and the appropriate degree of freedom, but by clicking it across. We can see that as we inputted the same coefficients to start with, our results are equivalent, and we see that for the OLS, we have got three significant factors. Our S&P 500 returns do contribute positively to BlackRock returns with a beta significantly higher than 0 and significantly higher than 1, meaning that BlackRock is probably leveraged. What also reinforces this claim is that treasury bonds have a negative impact on BlackRock returns, meaning that perhaps BlackRock leverages by short selling bonds or just attracting leverage from banks where interest rates are correlated with bond yields, and it's also slightly negatively exposed to oil, with gold having little to no exposure. And now let's see how the results would change, or would they, for different values of lambda for the LASSO model. Let's specify our LASSO optimization task. We need to go data solver and specify the following. We want our loss to be minimized by changing the cells with the LASSO coefficients over here. And we might want some of them to be negative, so we can untick this, and we can click solve, keeping in mind that our lambda is now 0. And we see that for lambda of 0, LASSO coefficients are exactly the same as OLS coefficients, reinforcing the mathematical logic over there. However, if we start increasing our lambda, so if our lambda is quite large, for example, lambda would be 0.2, we can see that our penalty term is very large, meaning that our loss term is dominated by the penalty term instead of the residual sum squared term. So the model would be willing to increase the error of the model to avoid taking on that high of a penalty. So that would reduce the values of some of these coefficients. Let's see what it will do with such a high value of lambda respective to the initial conditions of the model. We can click solve and see that the model now only leaves one significant result, setting 2 of the coefficients to 0. And that's exactly why LASSO is called least absolute shrinkage selection operator. It shrinks the least significant factors, as it thinks, to zeros. And here we're only left with the market factor being significant. However, the beta is almost half of what it was in the OLS estimation. If we play around with lambda, for example, reduce it further to 0.05, we'll be able to see that the results are now slightly different. The beta is now back being higher than 1, and we still have got some non-zero coefficients for treasury bonds and gold. However, they are quite close to 0 in terms of their p-values being very, very close to 1. One of the problems you might encounter with LASSO model optimization is that the optimization algorithm is non-smooth, meaning that as you have got to add on absolute values, the gradient descent method might do a limited job in finding those local minima of the loss function. To help the model to converge to the optimal solution, we can run the optimization via 0, meaning that here we would converge to the OLS result, as you can see here, and then we can start anew by selecting a lambda value of, for example, 0.02, something we haven't checked yet. And here, for 0.02, we see a result that is most meaningful so far. We have got our oil exposure set to 0, our gold exposure is shrunk somewhat, whereas our treasury bond and S&P 500 coefficients are both reduced, however they remain significant, meaning that among those 4 factors, S&P 500 and treasury bonds are perhaps the most substantial in shaping BlackRock returns. And that's all there is for the LASSO least absolute shrinkage selection operator and its application in Excel. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel and consider supporting us on Patreon. Thank you very much, and stay tuned.